Hi everyone, my name is Hayden Dalton. I'm a PhD researcher at the University of Melbourne, and my talk today is about using the argon-argon technique for Kimberlite Geochronology, using some examples from Finnish kimberlites. So kimberlites are deeply derived volcanic rocks. They erupt explosively, causing steep-sided cone shapes like we see here, with obviously quite large craters as well. They're interesting for a number of reasons. The top three are kind of going to go through now. The first, of course, is that kimberlites are the primary host rocks to diamonds, and here we have an example of a diamond from Botswana. Kimberlites are also the deepest derived magmas on Earth, coming from a depth at least 200 kilometres beneath our feet. And with that, they also transport pieces of the deep mantle to Earth's surface where we can study it in more detail. And some of these xenoliths can be up to a metre in diameter. But despite this obvious scientific and even economic importance if you consider diamonds, kimberlites still remain enigmatic. We don't yet fully understand the where, the when, the how, or the why. The most important piece of the puzzle, I think, is determining when kimberlites were emplaced. And with that in mind, I'm just going to go through briefly now the three most common geochronometers used in kimberlite studies. The first is the uranium-lead system applied to perovskite grains. This is done using laser ablation or isotope dilution techniques. Another method is to use the rubidium-strontium system. This is commonly applied to mica macrocrysts or xenocrysts that are derived from the mantle that the kimberlite passes through, but the system is reset upon entrainment, so you get a sure emplacement age. Then we have the argon-argon system, which can't be applied to xenocrystic mica, but can be applied to mica phenocryst or ground mass mica that crystallize directly from the melt and give us the true emplacement age. So my study has looked at kimberlites from Finland. There are two occurrences. There's the Kuusamo occurrence in the northeast of Finland and the Kaivokuopio field in the southeast of Finland. My samples were kind of like phlogic mica, and they have quite a big range in barium content from 0.5% to 21%, and then the potassium content sort of varies accordingly with that. So high barium content means lower potassium content, for example. My approach was to use an Argus-6 mass spectrometer using heating analyses, and we used multiple aliquots per sample to try and reproduce the numbers we were getting for individual aliquots. So in terms of results, we often think that the Plateau age is the gold standard for argon-argon dating. But I was always curious, is this really the true age? Is it an accurate age? We know it's precise, but is it accurate? Plateau ages are hard to come by for some samples. In my case, these two samples I'm going to show you now were partially chloratized or considerably chloratized mica, and you can see that the spectra are quite disturbed in these two examples. These two samples, the mica was actually in really good condition, but we still couldn't quite get a plateau despite the quite even and flat release spectrum you can see there. And then we have quite a number of plateau ages that are evidently very precise. So for example, the one on the left there, 764.6 plus or minus 0.9 million years. The one here, we're almost at 1.2 billion years plus or minus 1.5 million years. So again, the plateau ages are precise, but are they accurate? We'll get to that. And then we have one more example where the release spectra is completely flat, and again, a very precise age. So my study was comparing the argon-argon technique with the rubidium-strontium technique with the uranium-lead technique to try and understand, is there a best approach? Is there one way or another to get a good age for a kimberlite, and what's the most straightforward and time efficient? And this work was published in December last year. I'm going to go through some of those results with you now. So starting with the plateau ages, you can see a number of these symbols don't even have the error bars visible because the error itself is so low, the ages are so precise. So these are all the plateau ages. And then if we compare that with the total gas ages, so the total gas age is the aggregate age for all the heating steps weighted by the amount of 39 argon released in each step. What's interesting to note here is that in a lot of cases, in almost all the cases, the total gas age is lower than the plateau age, except for this one case, where the plateau age and total gas age overlap with an error. So what about the rubidium strontium ages? How do they compare? Now again, reminding you, total gas age is younger than the plateau ages, but the total gas ages overlap with the rubidium strontium ages in almost every case, which is interesting. Now, if you look at the uranium lead perovskite ages, again, total gas age is younger than plateau ages, rubidium strontium ages overlap with total gas ages, and so do all the uranium lead perovskite ages. So there's only one case where the plateau age, the total gas age for argon-argon system overlap with the rubidium strontium and the uranium lead perovskite age, which indicates that plateau ages are apparently older than other ages except for this one case. So why is that? Well, could it be due to extraneous argon, either excess argon, which is incorporated into rocks or minerals by non-radiogenic processes, or inherited argon, where we have radiogenic argon included from contamination from older material or mantle material, for example, that could be left over from a previous event? Or could it be due to recoil, either recoil loss of argon or recoil distribution? So recoil occurs when the samples are irradiated, the neutrons are fired at our sample, and argon atoms are redistributed or lost from the grains. So if it was extraneous argon, we probably wouldn't expect to see the total gas ages overlap with the rubidium strontium and uranium lead ages. So we can potentially exclude that as being the key factor here. So what about recoil? Now, if we look at the two types of spectra we have for plateau ages, we have a lot of cases where there are steps up before we reach the plateau. And then we have, I guess, the ideal case where the release spectrum is completely flat. And in this case, there's no evidence for any recoil effects in the release spectrum. And as a result, the plateau age is consistent with the uranium lead and the rubidium strontium age, and also the total gas age. So all of the four different ages we're comparing here overlap. But in the other cases, we're suspecting that the 39 argon budget is depleted in these early steps due to recoil, which means your subsequent steps have got elevated 40-39 argon ratios, which results in this apparently old plateau ages. These plateau ages that were older than total gas age, rubidium strontium age, and the uranium lead perovskite age. So that's what we think it could be. Now, if it was recoil loss, that would mean that any loss of 39 argon has been balanced by the loss of 40 argon. Or if it's redistribution, then potentially this redistribution of the argon has caused 39 argon to be released preferentially in those early steps relative to 40 argon. It's a possibility. So what's the outcome of this work? Well, it's clear that the argon-argon technique can produce accurate and very precise emplacement ages for kimberlites. Younger apparent ages in the early heading steps prior to the plateau, we'd recommend that you interpret those with caution, because it is possible that the plateau age could be too old, especially when we're comparing it with the ages from other techniques. So if there is this discordance, then our recommendation is that you can utilize the total gas age to get a better approximation of the true emplacement age for that kimberlite. Also, what I've realized, and it might seem obvious, but the grain selection is really critical. If you can use coarse phenocrysts, that really helps, and they tend to yield the best results, but also use grains that don't have any signs of chlorophyzation or any alteration on the margins, because even grains that had the most subtle of alteration still had very disturbed spectrum. Thank you for listening, and if you've got any questions, do let me know.